For security verification, please enter your passcode followed by the pound key.
Thank you. At the tone, you will be the third
caller in the conference. To mute or unmute your line during the call, please press *6 at any time.
Session. The topic of today's webinar is all object-oriented programming for hardware verification. We had got over 500 registrations, so we want to thank you for high interest and for in the beginning, we want everybody have a chance to listen to the complete presentation, so we don't want the people who join late skip the beginning. So for that reason, let me give a minute or two while I'll go through all the background. And for those who's not familiar with the company yet, we have more than 20 years experience in EDA with direct offices in Europe, United States, Canada, China, and recently in Japan. Our focus is verification solutions, simulation solutions for Verilog, VHDL, System Verilog, and System C. And hardware-assisted verification solutions is also something that we develop here at ALDEC. So hardware acceleration and prototyping, as well as software-hardware co-verification for embedded CPUs. If you go to aldec.com website, a few interesting things you may find there. Recorded AVMS session, including this session. We will post it in about 2 weeks. However, if you need it earlier, you can contact me. We'll get it to you early, the recording and examples. Also, you can download 20-day evaluation license. Well, the software and evaluation license you will get automatically if you fill up the form. So this is in case you want to try the examples we'll be demoing at this session. And you can get some other interesting things too. Again, before we'll start this presentation, what I recommend that everybody switches to the full screen mode. To do so, you have to press function 5, F5 key on your keyboard. Also, we'll put everybody on mute. And if you have any questions, please go ahead and type them into questions and answers panel. This is on your lower right corner. We won't get until answers until the end of the presentation. So at that time, we will unmute everybody, and Mike will answer all questions from the queue, and also some other live questions that you will be able to ask over the phone in case you join over the phone. And also, if you have a chance to dial in using your telephone, please do so, because the web audio broadcasting, you may experience some delay. So if you have a chance, please dial in. And now let me switch to the main presentation, and Mike will explain. We'll go through overview, and okay, Mike, let me pass it over to you.
Okay, thank you, Igor. So I always like to give an overview of what we're doing so that you basically know when I'm almost done. What I want to walk through here is sort of the 10,000-foot view of object-oriented programming, and we'll go down in lightning every now and then, and lightning down to the ground and show some actual code. But what I want to try to get across is that it's not that difficult. It should be a fairly good and obvious extension of what you're doing now. So I'd like to start out by talking about what it is, how it is I view a general. So this is like the mid to low level of a verification system. Is you have a generator and a checker, and then below that you have a driver and monitor. You may call it a BFM, you may call it other things, but fundamentally you have something generating stimulus, you have something checking. And the point is that this is always what you're going to have, regardless of what you program in Verilog, Vera, E, Specman, whatever. We're just going to try to objectify it, I guess. So, the first thing that object-oriented programming does is it helps you think about the data and the functions that work on the data together. Beforehand, code had been separated from data. It's called procedural code, and you had data structures, which are basically just groupings, clumpings of data, and then you had procedures that operate on them. Object-oriented programming changed that. It was actually back in '67, Simula, that did that, where they said, let's put the functions and the data together and put them into one clump so they travel together, so it's easier to make it consistent, as it were. So now the other thing it does is it bounds what you can do with that data, because if it's not in a function, you can't do it. So again, grounding down to reality for a little bit, looking at the driver side of a verification system, a driver basically sends data. So it would seem logical, and that's some sort of a state, obviously, because it's going to wiggle the wires. So let's take a look at how one might want to do a driver in object-oriented programming as opposed to procedures. So over here on the left-hand side, we talk about procedural coding. And this could be the same whether or not what language you're working in that is not object-oriented. You have a series. You first define your module or your structure. And here I'm looking at USB, so I only have B plus and D minus, which are the two wires in USB. And like most drivers, you have some sort of initialization. USB has something called enumeration, which is sort of like a bring up out of reset-y thingy. And then you're going to send a packet. You know, you've got some set of data. USB happens to have 4 different types of data, and they basically just blast the bytes along. So in usage, so this is how you might actually use it, is you create one of them, and then you call your functions passing in the address of the structure so that it knew what its state is. And then this one is actually just sending in some data. So let's go look at the data abstraction side. And there's a reason I'm calling the word data abstraction versus object-oriented programming, and that we'll get in on the next slide. But packing your data and your functions together is data abstraction. It's not object-oriented programming. It's the first step towards our object-oriented programming. But as we'll see in the next slide, you have to add something else called virtual functions. So here you define your structure, and there's our good 2 wires, D plus D minus. But we also go and put the function declarations right in here. They're the same without having this driver come in as the first parameter. And that's a little weird, a little strange at first. And you can see your usage is almost the same. You say, you know, build me one of them, and then I say driver dotted net. I don't need to say address of driver. I don't need to put the data structure in because it's already built into this call. So that's the first weird thing about data abstraction, or the step to object-oriented programming. What's happening under the covers, of course, is the compiler is saying, yeah, right, it's a global function called init, and I'm going to push in the driver as the first parameter. There's no magic here. It's just the compiler doing that to make it easier for you. So that's how we package the data and the functions together. So now we're going to step off into the slippery, slidey slope of object-oriented programming. And that's when you start to get virtual functions. Virtual functions are basically a function pointer. They're a variable which says what function you're going to call at runtime as a function of what object you created. And the trick is that you've separated the creation code from the code that's going to use the data. Well, the next slide will show some examples. And that allows the user code to be able to rely on what the function is supposed to do, not how it's supposed to do it. If the function is send data, or if the function is get data, it just is. And what actual object's implementing that is not concerned to the function that's actually saying, now is the time to get the data. So I like to call it the I don't know function, because a virtual function is, I don't know, this may be different later. And as I talked about it separates the concern of gathering something up and then doing something with what you gathered, or vice versa, creating something and then doing something with what you created. So that's one of the main things for virtual functions. So monitors have that property. Monitors have the property that they look at the wires, they do their wire thing, And then they have to do something with the data structure that they created. Hey, I converted this wire wiggling into an Ethernet packet, or into a USB packet, or into a video frame. So that's a good candidate for object-oriented programming and virtual functions. So let's again look at how one might declare it. So here I have a USB monitor, and I got my two favorite wires, and I have a start monitor thread. And that's going to probably run a background thread that's going to watch the wires. And then what happens here is it's a virtual function that says packet completed. So the monitor's job is to watch the wire wiggling and then convert that into a length and data. Probably should have a type too, now that I think about it. So a type of length and data. It says, hey, look, I found this type of transaction. Here's the data bytes, and here's how long they are. It doesn't care what you do with it. If you drop it on the floor. But it's useful to separate who's wiggling the wires from what you do once you've converted that into a higher level piece of logic, a higher level block. So, for example, here's one that is just going to print out the packet that we get. So it says, you say, struct USB monitor is a public USB monitor. That was the guy on the left. And it's going to what's called override this method. And again, there's no magic here. All the compiler is going to do at runtime is it's going to take wherever it built this code, and it's going to stick it into the structure that left a hole here. So what this virtual function says is put 4 bytes, or I guess 8 if you're on a UX64 machine, and leave a hole for me to call a function. And the value that's in this hole will tell you what function to call at runtime. No magic. And this particular one will just print out the data. You could, let's see, in this case I'm going to hook a checker up to it. So this particular one, again, it's a USB monitor. It's going to override the method, but what I'm going to do is I'm supposing I have some data member in me called checker. And I'm going to tell it, hey, check, here's some length in data. Something's happening. Now, what I tend to use for real in most of the work I do is building a channel in between the monitor and the checker. And just a FIFO, it's a fancy name to call a FIFO. And what this will do is it just puts the data into the channel, so that way the checker can get to it when it wants to. So you're decoupling when the monitor picks it up from when the checker actually does the data. We'll talk a little bit more about this later, but this is the basis of the trust code that I've written that's open source. And it's also the same thing for VMN and AVM. They just call it transactions and give it even fancier terms. So,
Mike, where checker and channel are described or are declared? Checker underscore and channel underscore variables.
Yeah, these are, in the essence of me trying to be clean, I suppose I could have put them right underneath here, but they are new data members added by this subclass. So I could have put the channel one in here, and I should have put the checker one here. Something I haven't talked about, and I won't talk about in this presentation, is called the constructor. When you create one of these structures, you often give it all the parameters. And in this case, the parameter would probably be a checker, if we're going to do this USB monitor checker. And in this case, the parameter on its constructor would probably be what channel do you want me to put it into. Constructors are just a fancy way for saying you're initializing the structure. But yes, you're right, those come in generally in the constructor. Whenever you see underscore, that's generally my indication that it's a data member. That's attention. Okay, so we're basically into object-oriented programming now. We put the function and the object together, and we've now started to use virtual functions, which are really just function pointers. They're just a variable that gets executed at runtime. One of the things you can do is not have any data in the base class and have all virtual functions. And what that allows you to do is to say, look, I don't care what data you use to get your job done, but here's the methods that I expect every data, every structure of this name to take. So, for example, if you had a checker class and you said, wait for completion, that is what I should be able to do with every checker. Or suppose you had another class that's called printable object, and you had a virtual function called print. You would not have any data because you didn't know what it would be printing, but you expect every printable object to be able to be printed. So you'd put a print virtual method in. And this is actually where the main power of object-oriented programming comes in, is not only can you separate concerns, but you can say this is the way it should behave, and that allows you to reason about the code. So we'll go down into something which I call a test irritator, which is you always have background. You should have background traffic in the test that you're running. So your main thing that you're concentrating on, then you have background traffic. Well, it'd be nice to just have a standard interface for background traffic. So it's like, well, I don't care really what it is. I don't really care what it's doing because it's just background traffic. I just want to be able to say, yeah, go, do your funky thing, background traffic. So in the Trust framework that I've built, Robert Eckendall and I have built, there's something called an irritator. And that has these methods, and a couple slightly other ones. But as you can see, they don't do anything. They just say, hey, out of reset, start, wait for completion, stop. But the point is that you can have a bunch of these objects in a list or something and say, hey, I'm going to start all the background traffic. So I'm just going to call the start on all of them. And then eventually I'm going to call the stop on all of them when I've decided my test is done. And then I'm going to call their wait for completion. And so it's a good way to, again, separate concerns and lay out an interface, a way they must behave. So here we go. We're gonna make one of them. This is USB irritator one, and I actually have these in a couple of my past lives. So this particular one was designed to generate USB background traffic. So it would, what's called override, that's a fancy word, it would override all these methods, and then it would do what it needs to do for USB traffic. USB has an out-of-reset concept. It has a sort of initialization concept where the wires have to be pulled the right magic way for the right amount of time. And then you can start sending data. Just as similarly, I could have done this with PCIe. And we have one of these in the place I'm working right now, where we have a background PCIe reader and writer, where we set it up with some address ranges, and it's doing its thing in the background while I'm trying to do my work. And again, it follows the same interface. So in my test, I just have a pointer to an irritator. I don't really care that it's PCIe, because I know how to call it, I know how to work with it. In the past, I've also done Ethernet irritators, where again, the concept is exactly the same. It has a well-known interface. I really don't care how it's getting its job done. It's just generating some background traffic for me, and of course doing all of its checking and stuff like that. And it's object-oriented programming, and specifically, these are called pure virtual to be fancy. These are the pure virtual methods that set up that interface that say this is how it has to behave.
Now, Mike, you call it irritator class. However, in the screenshot, we can see that it's actually a structure and not a class. Why is that?
Okay, good point. What Igor is talking about is right here. This word says struct instead of class. In C++, which is what this example is, struct and class are pretty much the same thing. Not true in System Verilog, but in C++, a struct is a public class. And what that means is these methods here, since I get my little dotty dot here working, there we go. These methods can be called by anybody who has access to your irritator. C++ and most object-oriented programming languages allow you to have other access scopes called protected and private, which we can talk about in the advanced OOP class. But what a struct does is it says the default scope is public for all these guys, so that you don't have to worry. Normally, if I was going to do this in the class fancy way, I would say class irritator, and then right down underneath here before this virtual, I would say public, which would say, hey, these are all public. But by making it a struct, I'm basically implying that. Plus, it shows you that it's nothing fancy. If you've ever worked in C, it's the same old C structure. Good question.
Okay, clear.
Alrighty. So now that we've gotten our feet wet in object-oriented programming, we're going to get a little bit more complicated, and feel free to kick back and sort of relax on this part, because this is more methodology, but it's what object-oriented programming can do for you. So in the stuff I've done, Truss, there's something called a verification component, and you can see this is the full-up guts and glory of its interface. So in my truss hierarchy, this test component, irritator, watchdog timer, test bench, all these guys are verification components. They all have this interface. And that's useful because that way the verification top can say, look, I know the phases, I know the dance, I know how to interact with them. I don't know what they're doing, but I do know this is how I should talk to them. So I have this as a base class for all these objects here. And let me spend a few seconds talking about why I built this sort of a test system. You may or may not have something similar to this. The first thing to note is I have a test bench, and that's mainly there to be the interface into the HDL. And I have this for System Verilog as well. There's a Truss System Verilog as well. And its job is to provide all the monitors, drivers, and checkers. It provides the hook to the actual hardware, all the wire handling stuff, and it provides to the test all the monitors and drivers and the things you might want to do, sort of the total transitive closure, as it were, of what the DUT is capable of doing. And the reason I did this, I used to not do this in that big of a test bench. The reason for it is if you want to start to have traffic that crosses interfaces, you're going to want to have all your interfaces down in your test bench. You're not going to want to have your test keep building different interfaces because it makes a lot of redundant code in there. So then I have a test, and really its whole job in life is just to stitch up and to coordinate between what I call test components and irritators. We've talked about irritators before, background traffic. Test component is the foreground traffic. It's the thing you're interested in. It's the thing you're doing. So the test's job is to provide to the test component the monitors, drivers, checkers, generators, whatever pieces it needs of the test bench. And again, this is separation of concerns. It's a common OP theme, where the test component only knows that, hey, somebody gave me a driver, somebody gave me a checker. I have no idea if this is one of 500 or one of 5,000 or the only one on a DUT. All I know is this is my job. Given a checker, given a generator, I can do my job. So the test's job is to basically be the stitcher in between what your DUT can do and what a test component or an irritator want to do. I have a watchdog timer as well. Fairly simple. It does the classic count number of cycles and then scream bloody murder if it goes off and your test isn't completed. I call this the impolite path. The normal everyday wait for completion is the polite path, but if you waited too long, the watchdog timer will come in and shut you down. Okay. So that's sort of what I use as a methodology, just to sort of explain how I fold object-oriented programming into a methodology for verification. Oh, didn't talk about the verification top. One of the things that I run, both in C++ and System Verilog, is a common verification top. It runs the exact same sequence of steps on the test bench, the test, and the watchdog timer, independent of what the test is, what the test bench is, and we know what the watchdog timer is, but the point is that this is a canonical definition of how to run a test, when a test is done, how to start it, how to shut it down. And I call that the dance, and I'm hoping that's the next slide. Yeah, woohoo! Remember this. So I could not come up with a better term. Robert and I tried, but the dance is the term we came up with for the series of steps that you want to do, regardless of what your test or your test bench is, to build, run, and shut down a verification system. So let me just walk through those. Take a breath, look at it for a little bit. Ignore the eye chart on the right over here. This is showing it from a code level perspective, and this is the other side is showing it from an object or event perspective. Again, the reason I put that up there is so that if you download this presentation, you can look at it slower and say, okay, I understand, or no, I don't. I got to send Mike some email because I don't know what he's talking about. It's fine. So, the verification top, the first thing it does is it creates test, watchdog, and the test bench. Obviously, which of these it creates, what specific test and test bench is some of what the building system does for Truss, because obviously you will be building a different test for each test. The next thing it does is it tells them to randomize. There's supposed to be a wire going to the test bench randomized. Oh well. It does. It lets the test bench randomize too. Then we actually have what I call the main test run phase of the system, which is time zero setup, which a lot of times you'll have pull-ups, pull-downs, configuration pins, stuff that you need to do before you pull the chip out of reset. That's what happens here. And then the main test instructs the test and the test bench to pull the chip out of reset. And the reason I gave both the test and the test bench is that sometimes you want to let the test bench bring the chip up. Sometimes you want to let the test bring the chip up. Sometimes your chip will have multiple levels of reset. In fact, most chips do nowadays, where you have a main chip level reset, and then you'll have some individual I/O level resets where you're setting up different functionality, and those have their own resets. So that's why everybody gets a crack at reset. Then the simple little 5-letter thing, start, is actually where all the fun stuff happens. That's where the tests run, the threads run, things happen. And then they all spawn their threads. And then the verification top immediately goes back to wait for completion. And it just waits for the test and the test bench to say, yeah, we're done. And then after they politely say they're done, it calls report. And in the systems that I've built, the report basically sweeps through all the checkers and all the generators to make sure that they think they've done everything they should have done. That's useful in case one of them didn't complete. And if one of them didn't complete, it's probably because you came in from this area, which is the timeout path. So the watchdog knows how to shut down the system. It communicates with the verification top, so that if you run out of time, it will go in and impolitely shut down the system, but run the same reporting mechanism, again, so that you can find out who may have hung up, right? If 15 out of 20 guys say, yeah, we're completed, all you have to do is look at the 5 that said they didn't, and then you have a chance of figuring out, all right, it's one of these 5 that had a problem. I'm not going to talk too much about this. Again, this is just for you to download, but this is the actual method or code level view of that dance. So we'll go to another eye chart here, which is the painfully detailed dance. Sorry. Again, just kick back, relax, sort of get the gestalt of the whole thing. Don't kill yourself here. But this is the view from your test. Sort of, ignoring the whole verification top, test bench, that sort of stuff. This is what your test should be looking at towards how to design a test component, what it should do. There are examples of this on the web that I have up there, and Igor will be going to an example as well. So it just looks big and ugly. It's actually not that complicated. Most of these just forward or do 3 or 4 line things. Again, that's another concept of object-oriented programming, is you want to package up functionality into objects that do one thing and one thing well, i.e. UART, UART generation, Ethernet broadcasts, whatever, so that you can reason about what each little piece does and not have to worry about where else it's tangled up to. So that's pretty much it. This is the slightly more complicated irritator dance, which is another form of the test component dance. And the only difference is basically this loop right here, where an irritator runs in a loop as opposed to a test component, which does a one-shot, which sort of makes sense, right? Your test component does its thing and it's completed. An irritator just keeps doing its thing until somebody else tells it to stop. So that's about it. Let me quick try to go with a summary. Hopefully most of you guys stayed with me here. It's not really that much new. OOP is just a little bit of funky syntax and a large amount of thinking about the problem. How do you break it down? It's not a trivial process. It is almost definitely 2 or 3 years before, after you've been coding it for a while, that you go, oh yeah, that makes sense. And it's okay. It's what happens. I've been coding OOP for almost 17 years now, so I understand it takes several years. Again, it's not different. It's just different packaging so that you have a chance of understanding the code and possibly reusing it. And the website has forums, other stuff for you to play with. This is the book that describes a lot of the stuff we've been talking about. I also have a book on System Verilog, and just in case you're wondering, no, I don't make much money on this. It's only a couple bucks a book. I'm not sure who makes all the money, but whatever. It's a learning thing. So I guess now we'll turn it over to Igor.
Thanks, Mike, and we're about done here. The UART example, now, do you, Mike, have time now?
Yeah, keep going. Nobody's kicked me out of the conference, so keep going.
So UART example, this is one of the examples from Mike's book, Mike's and Robert's book, Middle Complexity. So he actually demonstrates with this example, and this is something you can download from trusster.com, or you can just request me, and I'll send you a version of this example. So with this example, basically illustrates what Mike just spoke through. So as you can see, basic test component, the one that he mentioned, he had in all of his examples, and this test component creates a generator and a generator agent, and the reason for separate two blocks for it is so that one is independent of the implementation of specific implementation of UART 16550 example, and this is again for portability reason. Well, the core maybe of the example is here. So we have a UART 16550 core, and also, well, Wishbone driver was used. The Wishbone interface was used, kind of standard interface for all open IP cores that you can download from openipcores.org. So the test bench was using this Wishbone interface to access it, and as you can see, generator agent is going through an SFM agent, and SFM here is a software functional model, which now calls TEAL memory write function, and what it does, it updates register values in the actual hardware in Verilog module. And also the outcome of this UART TX, RX signals are checked with UART BFM block, and also with monitors such as UART checker agent and UART checker. So UART checker knows what the expected values of on TX and RX should be, and what are the actual values. So it compares those and signals to the test bench if there are any problems with it. Now that we know that, let's switch to the real example. I will share my Riviera view and explain how to run that example in case you want to download it.
Scarily enough, it's actually working code.
Oh yeah. So right here, I believe if you download it, it may or may not be under hardware verification with C++ directory, but what you will have is you will have a TEAL and TRUSS two directories along with examples, and TEAL and TRUSS contains all the sources required to build TEAL and TRUSS modules. Examples, we have 3 examples in this directory. The simplest one, ALU, block UART, I will be using currently, and then the most complex is required UART example. So what we're going to do, also there is a README file, so everything is described, what you have to do in the README file. Let me use it quickly to get the the command that I need to execute in order to build, first of all, build TEAL TRUSS, and then to compile Verilog portion of the UART example, and then finally to run the simulation. So as you can see, the system is building this specifically for Riviera simulator. And now, so we see it compiled the file and simulation started. In the simulation log file, it's quite conveniently shows the current simulation time of the message, and then what blocks this message belongs to, then even the file where that message comes from was originated, and also the message itself, some information, and carries some information here. So that's quite a long example. While it is running, I want to switch also to the GUI so that we can see the Verilog structure a bit better. Let me terminate it in the middle. So right here, the design structure, everything is instantiated under the top level. So UART top is the UUT model itself. And now Wishbone driver, the one I mentioned, is just for interface purpose, so test bench is accessing UART through Wishbone. And Watchdog that Mike mentioned will terminate the example in case it runs too long, and if we want to modify that, we can do it pretty easily to change timeout value. So here what you can do is, from a hardware perspective, you can add, let's say, all signals from your test bench. And then if you run this example, you will be able to see values on those signals. And for a UART example, that would be quite naturally some, well, first of all, we see the wishbone interface signals right here, and also, let me stop it in the middle, and also some RX, TX signal, typical signal for UART. So not only you can see those comments right in this code, but you can actually compare it, and that's for debugging purpose only. You can compare it to what you see on the signal waveform, on the graphical waveform, and then you can debug your code and debug your example. And that's about it. That's we won't wait until this example is done. Again, two ways to download it, either from trusster.com or you can just request me and I'll send it to you. The example, let me switch back to the presentation slide. And I guess now we will open the Q&A session. So again, let us get to this question and answers panel, answer it first, and then we'll unmute everybody, and you'll be able to ask your questions interactively. Done. That's about it.
Beautiful. So that seemed, I tried to slow it down a bit. Is that better?
Oh,